And then I have a small bench here, like some pieces of fiber optics, so we can practice and see how it works in real condition. Can you all see the screen now? Put this over there. So this is what we're gonna do. We're just gonna do a short introduction of fiber optics in the aviation industry. We're gonna review the main parameters of the tool, how to use it, main menus, features, and then we're gonna see how to use it on a real case. In the introduction, we'll see the principle, how it works, the difference between the multi-mode and single-mode fibers, the typical issues you might face, as well as some example of the typical connectors you can also face. Just a quick introduction of fiber optics. So fiber optics is usually it's to transmit light. We use it in aviation mostly because it helps to transfer high volume of data, and it's not sensitive to any EMC. So that makes things easier in terms of like transferring so high video, for example, of some stuff like this, and as well, it's also it allows to do long distance with limited power. Then it comes with new challenges because in terms of maintenance, it's different than electrical wires. So it needs to be taken into account, and you have to care a little more about the connection point, which are the weak point of the link. So just so you know, a fiber optic is made of a core part, cladding part, and a coating, and usually above that you even have more protections, so the fiber does not get damaged. Everything goes, actually the light is guided within the core, so the refractive index of this is different enough between the core and the cladding, so when you send light in it, it will be like controlled, and there's no way for the light to get out of the fiber. So the only way to get out is to go to the very end where you expect the signal to be. Yeah, to mention, the core and cladding can be made either of glass or plastic. You can find different type of fiber. I think in your case you're gonna have mostly multi-mode. The single mode, multi-mode, just to make it simple. Single mode, usually they have a smaller core, very small core, so you propagate only one mode. Whether multi-mode, you have a bigger core, so you can propagate different modes. Usually you have to, the source for a single mode is always going to be a laser diode. Usually the cost is higher since it's very thin, and the core has to be controlled. The advantage is that the distances you can do could be like around and above 200 kilometers, and the rate you can transfer is very higher. So compared to multi-mode, you can use laser or LED as a source. The disadvantage is you have a higher attenuation. You can have some loss of the light, and the distances are usually below 2 kilometers, and bandwidth is 10 giga, which means that in most of cases multi-mode is enough for aviation purpose. A single mode would be mostly for telecommunication, where you really need long distance. On an aircraft, you don't really take the advantage of the long distance, but you take the advantage of the bandwidth that you can transfer, as well as the fact it's not sensitive to any other surrounding system that can pollute the EMC or radio and other systems. So in aeronautical environment, as I said, the maximum distance is almost always below 100 meters, which is the length of the aircraft. Most of the application on long distance are for the camera at the tail. And then you may have additional application on HUD for the video flow, sometime on the IFE for some of the, like from a group of seats, before it gets distributed to individual seats, you may have also fiber optics. You can have, like, compared to telecommunications, sometimes you have interconnection. They are usually, you never have two connectors within a distance of 1 meter. Still, you may have a lot of connectors on the way because of the plane is built by section, and sometimes the fiber is installed before they assemble the section, so then they assemble later. So you can have multiple connectors on the way, and this is important to mention because this is mostly the area where you may have some issues. Before you get broken fiber, usually you will face connector issues. On the other hand, you guys work in harsh environment, like a plane. You would have always moving structure. When the plane got in the air, you can have some movement, and then that could, in some situations, stress a little bit the fiber. Usually not, but if installation is correctly done and does not move, that's going to be okay. You have vibration, you have change of temperature, you may have liquid humidity coming, and that would interfere with the initial setup. And sometimes it's difficult to access, and that's also why we brought this tool, is because we can give the location, so you don't have to check all the connectors. You can pinpoint the exact one which is damaged. Since you have so this kind of connectors that you can find the high density one. Otherwise, you can also find smaller connectors. This is one example here, for example. So this kind of connectors is FC, typical, very classical telecommunication one. I think this one is Helio, so that would be Airbus standard, for example. So you have different connectors. So these are single, and you have some high density with multiple fiber optics. I don't know you have much of this, but in case you could have this in the aircraft. One recommendation is the less you disconnect and reconnect fiber optics, the better, because each time you disconnect and you reconnect, you may stress the connector, you may have some dust inside, so that may affect the global performance of the full transmission. So be careful, yes, not to induce other faults on other connectors. Be very careful when you manipulate fiber optics connectors. So the way it works is that basically a connector, you have a piece of fiber, another piece of fiber with the core and the core, and what you expect to have is to get a physical contact between the two and a perfect alignment. So that's the way you can transfer the maximum of light. So if you have any misalignment, you're going to lose part of it. So you're going to have what we call insertion loss. If you don't have physical contact, you will have possibly high reflection over there. So some light will not cross. Most of it will be reflected. So you have to ensure that. So that's an example of a PC fiber. So they have polished faces, and then all the connector, or the purpose of the connector is to make sure you have pressure. So you have you maintain physical contact. So most of the time you have little spring into the connector to maintain physical contact. And the purpose of the connector is also to guarantee you have perfect alignment. So you have core-to-core perfect matching, so maximum of light will go through. So obviously, if you don't have physical contact, you will lose some of the power. If you have misalignment, you will lose some power. And if you have something in between, like you may have, I don't know, whatever, water should be okay, but skydroll, dust, any other possible small parts, then you may lose also some of the light. Also, if you damage the connector, it's perfectly polished here. So if you have some dust inside, most probably when you're gonna connect, you may scratch this part. It's not perfectly polished anymore, and then you lose some light. So every small damage, every misalignment, every space of air in between is a source of a bad connection, and that would lead, maybe if you have one or two on the way, you don't have enough power at the end, so the system is not working anymore. So the PC are connectors like this, polished, and then you have UPC for ultra physical contact connector. So it's very like the quality of the surface is even better, so you avoid any reflection. And yeah, return loss is minus 50 dB. If I go on this APC connector, so they would have an angle. So putting an angle maximizes also the light which is transmitted from one side to another. So just to give you some examples. So every time the performance is even better. Another type of connectors you could have is what we call expanded beam. So instead of trying to get physical contact between the two, we can add some lens in between to expand the beam, which means that the section of light would be bigger, and that would allow less sensitivity to dust or any pollution on the connector. Usually you have a lot of this in case you have a lot of assembly, disassembly. So usually in commercial aircraft you don't have to open and connect back the connectors. The installation is done, and usually you don't have to touch it, like, except if you have an issue or you change a computer or something like this. So this is mostly used on military systems, where, for example, if you have a recognition pod to plug on a fighter, or if you have a laser designation pod, or any weapon system where you need high rate transmission with fiber optics, they use this because each time they install the system on the aircraft, they're gonna plug it, unplug, plug, unplug. So they want something which is less sensitive to any misalignment or any dust or any pollution, so they don't have to worry much about cleaning of the connectors. Just in case in your life, if you encounter this kind of expanded beam connector, it's a little bit more sophisticated, and they usually they're gonna work only for one specific wavelength, because you have a specific surface treatment to avoid any reflection on the lens. So these are kind of different connectors again that you can find. You mostly will find two sections of fiber in the industry. So the 2.5, which comes from the telecom, which is also the Airbus standard, which is called Helio. And you can find also a 1.25 millimeter. So this is the size of what we call the ferrule, so the ceramic part that is going to guarantee the alignment. So usually, when I show you this, like for example, so this is the fiber, and this is the white part is a ceramic part, like this. If I remove the protection. show you on another one. So you see, if I remove the protection on the top, the white part is a small ceramic insert, and this is what guarantees the perfect alignment. So that's why also in some situation, if you don't have the exact adapter to match, you have a small adapters that you have to manipulate with a lot of care. These small adapters here are there. They are small copper adapters where you can actually, so it's a 1.25 millimeter. So you can plug a 1.520 millimeter on one side, 1.520 millimeter on the other side. You have to maintain a little pressure to guarantee physical contact, and then you can run the test. So these are the small 1.25, and these are the 2.5. So you see they are a little bit bigger. Okay. So this is to guarantee that the two ceramic parts are perfectly aligned, and then you have to maintain the pressure also to guarantee that the light will not reflect. So you have to guarantee the physical contact between the two. So these are the two main standards you have in aviation. You may have additional ones. Some systems they use regular telecommunication equipment, so you have all different type of connectors, and we also provide some launch fiber with the tool. So you have the Helio 1, which is Airbus standard. So it's a regular FCPC that's going to so we call that launch fiber, so regular FCPC that you plug into the module, and then this is for aircraft side. And this is the Helio 1. You have 1.25 millimeter here. And you have the square one that you may find on other system, which is I think LC. I have to double check that. And you have the regular one, launch fiber, regular telecom connectors. In some cases, also Airbus, you can supply some special adapters to make the connection. They are not included in the kit. This is something that can be procured separately, specifically when you have multiple high density contactors to fit with them. And this is a military standard, so you should not see that more often with a specific size. I don't know why they were so creative, but so what we are going to look at is the performance of a connector is often given according to two parameters: insertion loss, basically the power you lose when you go through a connector, or where you go through a fault. So sometimes the connector is the issue itself, but sometimes if you have an improper bending radius, you can have a local loss of light. So this is insertion loss, and you can also look at return loss or reflectance. So that's when you have a connection, that's the light that's not going to go through, but that is going to be reflected. So as I mentioned, if you don't have physical contact, most of the light will be reflected. If you have physical contact, most of the light will go through. So these are the two parameters that are important to qualify the quality of a connection, or to qualify the level of damage you may have on the fiber. Okay. So important to notice, our tool does insertion loss measurement. We don't do return loss. Why that? Because insertion loss is going to work either for connector or fault. So that's the light that is going to go through a connector or a fault, and then we'll review that later. Return loss is another dimension that we don't necessarily need to perform when we do a troubleshooting. So insertion loss, again, is the ratio between the power you put in and the power you have out. And it's 10 log since it's given in dB. Reflectance is the light you got from reflection, so the Pref for reflection, compared to the power you put in. So, and again, it's minus 10 log, and it's also in dB. So you want the reflectance as lower as you can, because you want most of the light to go through the connector. Also, for you have some ideas like a typical insertion loss at a connector point would be between 0.2 and 0.5 dB. So that's what we are going to look at. Usually, specifically in aviation, you can tolerate big insertion loss as soon as you don't have insertion loss in all connectors, but 0.5 is still good. If you start to see minus 1 dB or minus 2 dB, then you may have something to fix. The return loss would range between minus 40 to minus 60 dB, but you don't have to worry much about these values. We're gonna come to the tool right now, having set up and refresh your mind with some physics. We're gonna see the different the different advantages, disadvantages. We're gonna see how to perform the analysis of OTDR graph, and we're gonna see how to use the tool. So this tool is called OTDR, Optical Time Domain Reflectometer, and it helps to measure insertion loss. So we're gonna scan the full fiber only from one end. So that's a big advantage because you don't have to access to both ends. You can check everything from one end, and we're gonna scan the whole link and see at each time we see a connector or a fault, we're gonna measure insertion loss and give you the position of the fault of the connector and the insertion loss level, so you can figure out what is the performance of each event, whether it's a connector or a fault. So you're gonna scan a full length, and maybe you have interconnect, possibly in between you have some damages, and you are going to be able to qualify whether it's okay or not okay to have this event over there according to the insertion loss given by the system. This is how it works. Basically, there's a pulse which is sent with usually we use a laser diode that goes through the fiber under test, and we look at everything that bounces back, every reflected light that would go back, and then it goes through the coupler, and then we have a photodiode detector where we can measure the amount of light that we have. Most of the time we use a photon counting, so it's a very low level of light that is collected by the system, because on a typical fiber optic you have very low what we say backscattered light, so light which is coming back naturally. You always have some photon, but very few that are coming back in the fiber, but I'll come to back earlier. And then based on that, we control the time where we send the pulse and the time when we read what bounces back. So it's very fast because it goes at the speed of light. And then we send the pulse. We open the window for the photodiodes that correspond to one physical point on the fiber optic. We measure the level of light, and then we go to next point. So we do it like, it's like we were cutting small slices of the fiber optic, and every time we look at what part of light has been reflected in a small piece of optical fiber. And then at the end we can process a graph like this, and this is what we are gonna analysis. So typical shape would be like a small fault like this, or reflectance like here, possibly a connector, bending radius connector, and a fiber. We'll review that, and the system will help you also to figure out what type of fault you have. So this is an example. So usually a graph will look like this. So you have distance, and you have the intensity of the power of light that we have. So we start for a certain level, and then we have a decrease of which is due, like it would be like with no issue you would have just a small slope, just because you have a normal loss into the fiber. You will see that in our case for aviation, since we are working on very small distance, this will look flat because the distance are so small that we don't have much attenuation. So this is what you would see on kilometers. On an aircraft, this should be almost flat. Then when you have a connector, you may have a peak because you have a lot of lights coming back, a lot of photons are going to bounce back, because you never have a perfect physical contact, so some light will be reflected at the connection point, and that will create a peak. The eye of this peak is the reflectance, coming back to what I mentioned, and so you can measure the ratio between what you have in and what comes back, and it gives you the reflectance. And then after that, usually you have a fall, so you have lost some light because some has been reflected. And the difference that you have here between this and this, so you take the two parallel of the slope, okay, and the gap here, the step, is called insertion loss. So this is what we are going to look at, and that gives you the power you lost at this location, okay. So this is another example of a load. For example, load would be if you compress the fiber. I don't think you're gonna have much of these cases, but in case you know, it will look like this: small reflection and again a small insertion loss. Improper bending radius. So if your fiber optic would not respect the minimum bending radius, so you would have just a drop with no reflection, just because the light is going. If you have improper bending radius, all the light will not stay in the core. But then some part of the light will escape the core, so you lose the light, but it goes out of the fiber. It will mostly propagate into the into the air outside, or into the shield, the protection, or whatever. But you don't see that light anymore. It's gone. And usually at the end you have something crazy with a lot of reflectance, which is end of the fiber. It could be also on equipment, so I'll show you some examples. So this is what I was mentioning. So the insertion loss is the step you have here, and the reflectance is the eye of the peak, which is there. Important thing is that if you sum insertion loss at all points that you have, and in theory you add that to the attenuation, which is almost zero in our case because we have such small distances, so then you see the full attenuation of the line. So that means that if you add all the values, you know, maybe your full loss on this fiber might be, let's say, 3 dB. so you can still see whether it's still into a reasonable range or not. Because your issues are going to come either from one event, one damaged connector, for example, where you have huge loss, and then you don't have enough power on the other side for the equipment to work properly. Or sometimes it's just the sum of small faults. So you have a lot of small faults at different connection points, and because this fault plus this fault plus this fault plus this fault, it starts to create, and you lose too much light compared to what you need to get the correct transmission. So these are examples of faults. So improper connector, so that will lead to reflectance. Some light will bounce back. Some light will go there, and you see you have a lot of light here and very small here, and this will the typical graph that you will have with again reflectance here, insertion loss here. End of fiber, usually you have a lot of reflection because there's nothing there, so it will act partially as a mirror, and after you have a noisy signal because then there's nothing much, and then that's going to be the noise of the equipment itself. Improper fusion slice or fiber bend will do this S. Sometimes you have a ghost image, so don't be confused if you see additional peaks which appear to be after the optical fiber itself, after the fiber optics. You have let's say a 30-meter length in total, and maybe you see fault after 30 meters. Usually it's because you have a big reflection and some light is going to go back and forth into the fiber optics if you have a reflection. So just so you know, sometimes you see, maybe we'll face the case. Sometimes you have end of fiber and noise, and sometimes you can see one peak right in the middle of the noise. It's because maybe the light went through the fiber. You had a full reflection, it's coming back, and you have another fault. It goes back again in the other direction and come back to the meter. So just so you have this in mind, keep in mind the total length of the fiber optics you are checking, and don't get confused by potential peak that are above the length. Don't take that into consideration in case you see something suspicious. Okay, coming to the device itself. So the tool is made. All of our tools are made the same. You have one diagnostic box. So this is specific to fiber optics. This is controlled from one tablet. This tablet can be used with other tools that we offer. And then you have a bench of launch fibers. So as I said, the pure telecom one, which is there, Helio standard, and 1.25 standard here, and one additional that you may also have, I think, sometime on IF. The communication between the tablet and the device is with Bluetooth. You have to charge the module from this USB, micro USB plug. That's a power on-off button over there. And this is where you will plug the launch fiber that you will plug to the aircraft. Okay. We have a laser emitting diode here. So it's important not to run the test if there's nothing connected, or if you don't have the cap. because you have you won't see the light. It's infrared, and it could be dangerous. So that's why you have this symbol. It could be dangerous for your eyes. Okay. So think about this is a laser system inside. So always be careful while manipulating. Also be careful when you have the fiber on the other side. If the equipment is unplugged, the light will go through and will get out the fiber. And again, you don't see it, so be careful about that. So this is how to turn on the device. So just this button. Up, I have a light, I know it's turned on. If you plug the charger, you will have the charge light to tell you it's charging. And the tablet, the button is on the top here. You power the tablet. I switched it on earlier, so you can just sign in, there's no password. And it's a Windows tablet. So you use as a Windows device, and you have an Aer'Optic app which is there that you can launch. So you have different part numbers. I'm going to use this one, the 3304-1, which is the FC. And I brought some made a little setup with different types of connectors over there. So when you connect the FC connector, you have to be careful. There's a small part there. Okay. I don't know if you see it. Well, you will come and practice after. So you have to make sure to align it, and then you feel the spring, and then you can screw the system. Then I can do same over there. So it's not emitting. As soon as I don't run a test, I have no emission, so I can safely connect to it. I have to be careful when I do this. I have to find the and I can screw. No need to be too tight, but still to keep you remember the physical contact. So now I'm connected. I have a launch fiber here. I have a 3-meter fiber with FC connector and then ST connector. I have a ST-FC adapter, one other FC 3-meter fiber, and I just put an example of broken fiber on the other end, just to do it. So. The range of my the system I want to test is roughly like maybe something like less than 10 meters. So I have to know like roughly the length I'm going to test. This is one parameter I'm going to enter into the system. So this is the main interface. So I'm gonna run Aer'Optic from here. So it's this icon here. I double click. You also have a stylus available here if it's more convenient for you to use. And this is the main interface. So the play button is to run the test. record is to save measurements. You can export the file at XML or image. Okay, I need to connect to Aer'Optic. And then you have parameters over there. So I'm waiting for it to be connected. Okay, it says Aer'Optic's ready, so it's connected. So you see, I had to switch it off, I don't know why, just in case it's not connecting. Maybe I switch it on too early. So now I have the main interface over there. And I put this so you can see in the screen. So when I click the parameters button over there, this is the screen I have. So I can select the range in meter. So we said for us, in our case, it was I just have to find the keyboard. To find the keyboard, you can do a swap like this, and then force the keyboard to appear. And come back to the app here, and then I'll put, for example, 20 meter. It's gonna be enough.
We need to know the length of the cable first, is it? Roughly.
Yeah. And you put at least 5 meters more, so you're good to go. Insertion loss warning, I can stay with 0.2, for example, for the moment. So this is going to be your criteria to know whether this connector is considered good or not. And then you have resolution, you have 3 levels. You can do low, default, or high. I suggest to start with default. So the higher the resolution, the longer the test. So if you were to test a long fiber optics, maybe start with default, it's gonna be quicker. And if you need more resolution, then after you're sure that you cover the whole fiber and everything is okay, then you can do the high resolution one. So now I'm good, I can click OK. And yeah, just so you know, before I launch the test, I can give you some information in addition to that. Just so you know, the low resolution is going to be 1 point every 20 centimeters. Medium is going to be 1 point every 8 centimeters. And high is going to be 1 point every inch, every 2.5 centimeters. Okay? So this is very high resolution. You know exactly where the issue is. And that's the best for the best accuracy when you do measurements. But please start with medium or low first, just to have a quick scan, and then you can run the other test after. And this is one example of measurement. Obviously, this is an example with a lot of issues, lot of connection, lot of damages. And this is how it's going to look like. So you're going to have the graph on one side, distance and amplitude, okay, as I showed you before. I told you you're not going to have a slope because we don't have much attenuation. It's pretty flat. So this is a connector with good performance because it's almost the same level of light before and after. This is a connector with some damage because I see the difference here is a little bit bigger. This is improper bending radius. This is most probably a load, and so on. And you have all these events, and this is end of fiber over there. And the system tells you for each event, you will have a line on the graph, and you will have one line on the table that gives you the position, the event, the type, whether it's the event type, sorry, whether it's pass or fail, according to the criteria you put. And then you have this for all of the events that are catched by the system. So if I launch the test here, I just know I put the proper parameters, remember, 20 meter, and we check whether it's good or not. Maybe I'll change that. Insertion loss limit is 0.2. I say OK, and then now I can launch it. So this is when you have to be careful, because now I have a laser that is working over there, and now I have the graph which is going to be done. So it's scanning the points one by one. So you see some reflectance at the connection point. Okay, and you see a big drop, which is the end of the fiber. So now the system is still scanning. So you see small peaks because I have multiple reflection, as I mentioned to you earlier. But when you see this drop, you know that's a broken fiber or end of the fiber. So maybe I was too conservative by taking 20 meters, because the system is still working on it and I don't even have signal. So maybe I'm gonna do another run at 12 meters. It's gonna be enough, and I would have a full range. Okay. So let me change that to 12 meters. So I was 20. So you see, it's always better, like, to come back to your question, to put something longer. You figure out it's not too long to do it on a like average resolution, and then you can change after that. The tricky part is to, if the keyboard does not show by itself, you just have to do this, and then you get keyboard access over there, and you can come back here. So I'm putting just 12. Okay, and I'm gonna run it one more time. So I have another scan. Then there's no surprise, and the fiber. I'll wait for the system to stop. So you have measurement in progress here, and then as soon as it's done, it tells Aer'Optic's ready, and you have the list of the events. Okay. So the first connection point, the 0, is always this point. It's not this point. You don't need to care about this. We only care about this one. So the launch fiber are always the same size. Okay. So 0 is always this point. You see, in that case, I have a 0.3 insertion loss. Since my criteria was 0.2, it says failed. Actually, 0.3 is still very good, and we can play after to simulate some damages. Then I have the second connector about 3 meters after. So I told you I have a 3 meter fiber, and I have this connector now, which is 0.1. Then I have 3 more meters, which is this fiber, and then this connector, which is good. This is very good, even 0. And then I have this broken fiber. So you see in this example, we put a piece of paper so we don't have infrared light going over there. So I have the broken fiber at 8 meters from this point. Okay. If we want to simulate a fault, for example, I can unscrew a little bit this, so I reduce the physical contact. I'll see what's gonna happen. So I can launch it again.
Let's say the other end is connected to some component.
Yeah.
Do we have to disconnect that before we run the test?
It could help you to make sure that you have reached the end, but you don't necessarily have to. But it's gonna help you anyway because then you see end of fiber. So if that's the supposed length that you have, and then after, if you have any doubt, you can run the test from the other side too.
Because we don't want the equipment to be damaged from this.
Yes, that's why I tell you. Usually,
There
if
is
they-
no concern. There is no concern.
it's up to you to check that, whether it will be damaged or not. From my perspective, I think if the equipment is off,
It should
It's
be
a-
because
it's a low
it's run
voltage.
by light, it's
Yeah.
not by current.
It's not
yeah,
Okay.
exactly. But yeah, always better for you to double check that. Okay, so it's a mess because I created a big fault now. So I have many events. I can still see the different positions, even though the first one was not even seen because it's too. I created such a big fault that it's not positioning even the event at the right point, and it couldn't measure. Maybe if I go to higher resolution, let's see if I can have some.